Assalamualaikum warahmatullahi wabarakatuh. My name is FAREESHA MELIA binti Muhammad YUSUF and my partner name is AZURA binti Muhammad ANUAR. In this video, we are going to explain about the wave functions in the presence of forces. Enjoy! So I'm going to explain about the first equations. The wave function for a free electron changes with time according to the Schrödinger equations is stated as the first equation. So for the first equation, time-dependent pure wave that describe momentum and angular states and many other time-dependent wave functions that describe superpositions of momentum angular states are among the solutions to these equations. So these broad wave functions will all tend to spread out over time since they are superpositions of electrons with a variety of conceivable velocity. So as t approaches infinity, the position's uncertainty increases. The wave packet for flying electron, for example, that get increasingly spread out or highly localized wave functions that soon spread out in all directions. In nature, it is obvious that all electron wave functions do not spread out more and more in time. If an electron is present in an atom, it will remain there unless it is disturbed by an external force. Similarly, the wave function of an electron in a metal may spread out through the metal, but the electron will not escape unless there is some external influence. So for the second equation, the potential energy Ux of electron varies depending on their positions, leading to forces Fx equal to U0 in the bracket x. So we need to know how to alter the Schrödinger equation when these forces or potential are present in order to comprehend how wave function evolve in the presence of this force or potential. So consider the instant of a hydrogen atom where an electron potential energy is equal to the Coulomb potential from the electron. So with all of these explanation, it will give us an equation which is Ux equal to negative Ke square over x. So for the next slide, to see how the potential, which is Ux, should be incorporated into the Schrödinger equation, we need to consider the basic case of an electron with a definite momentum P traveling through a region where the potential energy is a constant but not zero. So for this situation, the electron and the electron total energy is now given as the first equation in this slide, which is E equal to P square over 2m plus U. So the electron should still be characterized as a pure wave with wavelength h over p because it still has momentum p. So however, based on the relationship between energy and frequency, we have anticipated that the frequency will now be in the second equation, which is f equal to E over h and equal to 1 over h in bracket p square over 2m plus u. Thus, the momentum angular state wave functions in a region of constant potential energy should be given in the third equation here in the slide, and which it reduced to our previous result when u equal to 0. So for the slide 4, looking at the first equation that I've mentioned before, which is I hash dv over dt. That equation, we can find that the left side now bring down a factor of p2 over 2m plus u, while the right side still only give us p2 over 2m times the original functions, the original wave functions. So to make the function, which is vp in bracket xt, solve the equations, we need to add u times the wave function to the right hand side. So this will give us the first equation that shows in this slide. So for the above equations, the wave function can depend on x, y, and z. So the equation include y and z derivative also will give us this equation.
Okay. In this video, I will share about time-independent Schrödinger equation so that you will understand what is time-independent Schrödinger equation. Okay, first of all, as you can see, this is time-independent equation that I state in this video. Actually, time-independent equation in this video is wave equation for matter waves in separable form. The solution in separable form are called stationary states. So that for stationary states, all probabilities are static and can be calculated from the time-independent wave function. Okay, from the previous equation, explicit solution to this equation cannot be written for an arbitrary potential energy function. A wave function must be well behaved because of its connection with probabilities. In particular, wave function must be everywhere finite, single value, and continuous. And for free particle, the separation constant energy become to total particle energy. So the wave function will change. However, with the introduction of forces, because particle momentum, K is no longer constant. This identification continues to valid when forces are present. Okay, thank you for your time. I hope you can easily understand what I discussed in this video about time-independent Schrodinger equation. Thank you.